Anybody have any homework questions? Okay. Well, so we got the stuff out of the way that we had to with units and prefixes and scientific notation. So now we're ready to go on to the first topic that I would call physics, kinematics of a particle in 1D. So I want to break that down a little bit because it's a long name. Kinematics of a particle in one dimension. So first, kinematics. So what does that mean? Kinematics is studying the motion of an object. You can think of it as just based on the things that you could figure out from watching a careful video of it. It's only describing the motion. It's not dealing with causes of motion, like how hard something pushed on it or pulled on it, or what its mass is. You couldn't tell from a video how hard something's pushing or pulling on something, or you can't tell what its mass is. But if you had a room with rulers all around, or a floor that's gridded out, you could figure out how far something moved in how much time. You could figure out based on that, you could figure out how fast it's moving from here to here. So all that we're doing at first is the stuff that you could calculate from watching a video. So this is describing motion, without considering the causes of the motion. This is the stuff you could calculate from a video. Okay, so that is, and just to get you ready for this is a pain, but the kinematics is the word that separates you from the kind of physics where you are dealing with the causes of the motion. And so kinematics as opposed to kinetics. Why they have to sound so similar, that's just a shame for all of us, but that's how it is. So kinematics has the extra ma in it. Ma, tell me. Hey, Ma, what's kinematics? Okay, so that's kinematics. Now what's a particle? I think probably most people, the first thought you would have is a particle is something that's really small, but that's really not, it's really not necessary that you do particle physics on things that are small. When people are doing calculations of planetary motion, they treat planets as particles. So what is it? So what is it that really boils down to? A particle. So a particle analysis is a way of thinking about an object when you don't care about the object's orientation. You don't care about the object's orientation. And when that's the case, you can treat, even if the object is really big, you can treat the object mathematically as if it doesn't have any length in any direction. So you treat it as if it has no length dimensions. It still can have mass when we get to kinetics, and we are talking about the causes of the motion, the mass and the forces and things. So although it does have mass, you just treat it like it's a little point moving around. And so why would we treat the motions of planets as particles? Because for the most part, in many analyses, we don't care about the orientation of a planet. We just want to know where it's going to be, relative to our sight lines here and there at different times. So if you're trying to track the motion of Jupiter and you don't care whether that big red eye is facing you or facing away from you, then you might as well just do a particle analysis. And then the last part of this long title is 1D. And 1D motion is motion where at any instant the object only has two choices of where to go. The easiest way to think about it, and the thing that we're almost exclusively going to be talking about here, is if something is restricted to move along a line. Okay. So if a particle, so imagine that's a straight line. And there's the particle that you're tracking. At any instant, at this instant here, it only has two choices about where it can go. It can go, you can think of it as forward and back, or what we're going to think about it as, once we start putting numbers to it, is positive or negative. Okay? But either way, it can't go up, it can't go down, it doesn't have all these choices of where to go along the whole chalkboard, it only has two. Okay? And one-dimensional motion doesn't have to be along a line. It just has to have that restriction to two choices in any location. So if you think about a bead sliding along a curved wire, that's also one-dimensional motion. Because right here, where can this bead go? It can only go that way or that way. And it doesn't, and that's true everywhere along, even though the path is perfect. Okay. So one-dimensional motion doesn't mean that it's moving along a straight line, although for us, those are the examples we're going to focus on. So a bead moving along a curved wire. Yeah. Yes, that's right. That's right. Yep. So yeah, so the idea of that is, so this line lives in, you know, you can describe this motion in, oh, yeah, that's, yes, you are correct. So what this means is the first topic that we're going to study is just describing the motion of things where we don't care about their orientation as it moves mainly along a line. Okay? So we're going to track the motion of objects as it moves along this known path. And the quantities, the measurable quantities, quantities, that's abbreviation, that we'll use are the position, lowercase p, the velocity, lowercase v, the acceleration, lowercase a, and the time, lowercase t. And so I have to define what all of these things mean. Okay, so let's say that, so I'm going to start by defining position. Let's say we have a train moving along train tracks. One of those like old-timey trains, because that's the only kind I know how to draw. Okay, so this train's going this direction. And we're treating it as a particle, which means we're treating it like it has no length dimension. So we have to boil down its location to a single point. And I guess I'm going to choose its center of mass to be that point. You know that symbol from like crash test dummies and commercials? That means center of mass. Okay, so at this instant, the train is going, you know, cruising along, and it's at a location, and we, as the people trying to measure its motion, we don't have any choice of where it is at this instant. But what we want to do is take that physical location and represent it numerically. And so to do that, you know, the question is, what do we need to do to assign a numeric position to that object's physical location? So once you choose a length scale, and almost all the calculations we're going to do in this class, we're going to use SI units. So our length measurements are going to be meters. Our time measurements are going to be seconds. Mass later is going to be in kilograms. So let's say we've already chosen our scale for length. We're going to use meters. what you have to do is choose first a physical location that you're going to call the 0 position, like a reference position. So a physical location corresponding to 0 position. And we can put that wherever we want. I'm going to put it here. Okay, so write a scripty little O for origin, but that's my 0 position. Okay, so that's the first step. And then the second thing we have to choose is we have to choose, so one of the directions in our one-dimensional motion we're going to call positive, and one we're going to call negative. And it doesn't matter which one you call which, but you have to choose that before it makes any sense to assign numbers to locations. So I'm going to call this choosing a positive direction. Or let's say choose a physical direction corresponding to positive. Well, since we're used to seeing numbers on a number line and the positives on a number line always go to the right, I'm going to do that here, but there's no reason that I have to do that. I'm going to choose my positive direction to be this way. That means my negative direction is this way. And now that I've done that, just count off how many meters it is from our 0 position to the train, the thing that we're looking at in this case. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's say it's 10 meters. So in the example above, the train is positioned 10 meters in the negative direction, from our 0. So the position is equal to negative 10 meters. Mm-hmm. So if I had chosen a different 0 position and or a different positive direction, the numbers associated with my positions would be totally different, you know? And the first time you see that, you're sort of like, well, what's the point then of doing this? But we're going to see that as long as you're consistent through your calculations about what your 0 position is and what your positive direction is, you can get a lot of really useful calculations out of these definitions. So that's why we're doing it. Yep. It doesn't have to be the starting position. It just has to be a reference. Okay, and we haven't seen any important distinction between those yet, but actually the starting position is going to be something else later on. So if you can wrap your head around that, it'll pay off later. the reference position can be anything. Like I could call that door the 0 position. Let's not do that because I was at that door. Let's say I can call that clock the 0 position. I was never standing over at the clock, but I can call that my 0 and measure all my other positions in reference to that. Yep. I imagine that those are actual meter sticks and I carefully measured. Or, it would be easier as if I had measured beforehand and then I could just see that the train passed by the mark that said 10 negative 10 next to it, Yep. Yeah. Yep. There will be some times later where I say this is what I want as the 0, this is what I want as the positive. But if I don't say that, then you can choose anything for those two. And notice that position is always, so position always has units of length. And the SI units are meters, lowercase m. Now, one thing I want to well, not yet. Okay, so let me just finish with what I'm doing here. So that's a position at a single instant. If you also choose an instant to correspond to 0 time, and the easiest way to think of that is turning on a stopwatch. Like when you turn on a stopwatch, what you're saying is right when my thumb hits it, that's what I'm going to call 0 time. And everything that happens after that is going to be assigned a time based on how long it's been since I hit the stopwatch. Okay. So if you do that, you can assign a positive time value to all future times. And the main reason we're going to do that is you can then write position as a function of time. Okay, so let me show you what this looks like. So for example, so here's the train track. Okay, and here's what I called 0. And let's say time equals 0 was when the train was at this location. Okay, it doesn't. The train doesn't have to be at zero position. It can be anywhere, but you just have to have a defined instant where you're turning on the stopwatch. And why did I make this so far away? Now I have to count all these meters. Okay, I lost count. 1, 2, 3, 6, 7, 8, 9, 10. So there's negative 10. There's negative 20. And then 21, negative 22. Okay, so when time is equal to 0, right when we turn on the stopwatch, the train is at position negative 22 meters. Okay. Let's say at time equals 1 second now. Where's the train? Now this is all stuff that you have to measure. So I'm just making this up. But let's say that we saw, now that we've defined this scale, we saw that the train was at position negative 15 meters. Okay. At time equals 2 seconds, let's say that the train was at position negative 10 meters. So let's say that's the instant that we were looking at before when we saw the train at negative 10. Let's do 1 more second. And then at t equals 3 seconds, the train is at position negative 2 meters. So what this lets us do is we can draw a graph where time is horizontal, time in seconds, and position is vertical in meters. And so let's say this is negative 10, negative 20. There's negative 22. Here's negative 2. And then the seconds, here's 1 second, 2 seconds, 3 seconds. We can draw this motion on this graph. At time equals 0, what was the position? Negative 22. That's what we saw here. At time 1 second, what was the position? 15. At 2 seconds, the position was negative 10. At 3 seconds, the position was negative 2. And so at every second, the train, there's some time that corresponds to some position. And you can graph those two together in a position versus time graph. So this is a position versus time graph of the function position as a function of time. Often this function, p is a function of time, will be a, you know, a known mathematical function. For example, you could have a case where the position as a function of time is equal to 5t plus 8. I just made that up. Okay, so what's the object's position at 0 time? And then, you know, I'll ask one more, I guess. What's the object's position when time is equal to 10 seconds? So how would you calculate those? Well, what that's saying is whatever time you want to look at, whether you want to look at that time, that instant that corresponds to time equals 0, or whether you want to look at 10 seconds after that instant, you just plug in those values for t, and this will give you the position of the object back. So what is the position of the object for this function when time is equal to 0? It's 5 times 0, which is 0, plus 8. So position is equal to 8 meters. And then what about at time 10 seconds? Yep, position is 58. Anybody have any questions right now about that? It's still pretty abstract. I think a lot of this stuff will start making more sense when we start doing examples. Yes. Mathematically, that would be fine, but in practice, that's an important question. Thanks for asking that. We're never going to use negative times. Not for any mathematical reason, we're just not going to. So your time equals 0 has to occur before the stuff that you're trying to investigate. Still, right. Yep. But we're just going to always set things up in a way that our times don't come out negative. That's really more convention than anything, but we'll never see negative times. All right, so the next thing I want to talk about is directional versus non-directional quantities. And I want to bring this up because we're going to be using position, velocity, and acceleration, and those are the meanings of those are slightly different than the meanings of the related things that we're used to talking about in our everyday life. So the things that are going to be important to us are these directional quantities. The things that we're more used to talking about are non-directional. Okay, so the directional quantity that we're going to, that I just brought up is position. And it's directional because the positive or negative sign tells you where you are in relation to, it tells you which direction you went from the 0 position. There's not really a non-directional version of position. I just leave that blank. But there is a related thing called displacement. I guess I'll write that as a lowercase d. And displacement tells you not only how far an object has moved in a certain amount of time, but which direction it's moved, because it has a positive or a negative sign. It's sort of related to, I mean, it's closely related to what we're used to talking about, which is distance. But if you said, so if you drove from the Twin Cities to Iowa, okay, to the, I don't, what's the nearest town in Iowa? So that's far, isn't it? Yeah. Okay, to the border. 100 miles, yeah, okay. So the distance to the border is 100 miles. The displacement from here to the border would depend on which direction you chose your positive direction. If you chose your positive direction going north, then your displacement would be negative 100. If you chose your positive direction going south, you'd be going in the positive direction and your displacement would be positive 100. So after displacement and distance, we're going to talk about velocity. That'll be with a lowercase v. And that's related to speed, but it's not the same thing. So again, if you drive to the Iowa border and back, and you go 60 miles an hour the whole way, your speed at any instant is 60 miles an hour. Your velocity, though, depends on which way you made your positive direction. So again, if your positive direction was north, then for the part where you're heading south, the first half of the trip, your velocity would be negative. For the second half of the trip where you're heading north again, your velocity would be positive. And then the last thing that we're going to, directional quantity that we're going to talk about is acceleration. That's a lowercase a. And that sort of relates to our non-directional idea of acceleration and deceleration. Now, decel. Okay, so with position, so far we've seen what that direction means, what the sign means. It tells you where you are in relation to what you defined as your 0 position. This is going to keep coming up with all of these, and I'm going to try to bring out those differences as we go. Mm-hmm. Yeah, if you chose this as your, it depends what you called your 0 position. Okay, yep. Your position is 0. Your displacement is also 0. And we'll define displacement carefully and stuff, but your distance is 200. Yeah, distance is always positive. So, yep. And if you, right. Okay, so let's do an example. So let's say here's your house. It's little, but it's nice. It's nice inside. And then here's a fire hydrant. And then here's your car. And let's say that from your house to the fire hydrant is 15 meters. And from the fire hydrant to your car is 10 meters. And let's say that you walk from your house to the car and then back to the fire hydrant. And let's say that going from the house to the car takes 5 seconds. Is that too little? Yeah, 25 meters. How long would that take? 15 seconds. And then from the car to the hydrant takes 10 seconds. So the first question is, if we define the zero position to be at the house, and the positive direction toward the car, and zero time at the instant when you leave the house, we want to sketch the position versus time graph. Everybody follow the idea here? So we have this motion that we, as the people measuring the motion, don't have any control over. We don't have any control over when the person, how long it takes for the person to go to the car, whether they go to the car, whether they go to the fire hydrant, how long that takes. But we do choose the zero position, and we choose when we start the stopwatch. And we're going to use that now to sketch this position versus time graph. And I think the easiest way to do this is I'm going to draw first a number line. And here's the zero position. That's the house. Here is the fire hydrant. And here's the car. So the first thing we have to do is come up with numeric labels, numeric positions representing the hydrant and the car. Well, we know that this is 0. And this is the positive direction. So what's the position of the hydrant if it's 15 meters in the positive direction from 0? Plus 15, yep. So I'm going to write that here. And then the car is, it isn't 10 meters in the positive direction from 0. It's 10 meters from this. So it's 25 meters in the positive direction from 0. What's its position? Plus 25. And now let's think about what the motion does. So the pedestrian starts at the house, walks over here, to the car and turns around, and then comes back to the fire hydrant. Okay. What does the stopwatch say? Remember, the stopwatch was started when the person started walking out of the house. What does the stopwatch say the instant the person gets to the car? 15 seconds. And what does the stopwatch say? So it takes another 10 seconds to get from the car to the hydrant. So what does the stopwatch say when the person gets back to the hydrant? 25 seconds. And now we just have all these, we have all these coordinates. You can think of it like this. I'm going to write a little table as like the time and the position. When time is equal to 0, what's the position? 0. When time is equal to 15 seconds, what's the position? 25. And when time is equal to 25, what's the position? 15, yep. Anybody have any questions about coming up with those values? So now I can plot these points. Time is always on the horizontal. Position is always on the vertical. So we have the point 0, 0. We have the point, I'll say 5, 10, 15, 20, 25. Yes? That's right. The displacement doesn't depend on time at all, unless, but I'll talk about displacement more later. Okay, so that's 5, 10, 15, 20, 25 seconds. And then the positions, we have 5, 10, 15, 20, 25. Okay, so our first point was 0, 0. Our second point is 15 seconds, so we know it's going to be along this line somewhere. And the position is 25, so it's 15, 25. And so just plot that point. And then the last one is at the time 25 seconds and the position 15. So there. I'll connect these so you can see. And then the graph, if you're, this is the only information that we have, but so you can connect these in some way. You can make them curvy or have a sharp break. I don't care about that. The graph of position versus time would look something like that. Any questions about that? Okay, so now let's do a part B. So we're going to look at the same motion, the same house and hydrant and car. But this time, we're going to call the position equals 0 the hydrant. The positive direction toward the house. And time equals 0, 5 seconds before the person leaves the house. So we didn't have the power to change anything about what the person does, but it is going to change the numbers somewhat. Okay, so let's go through the same analysis with this. I have a question. Yeah. It'll make negative positions, but as long as your 0 time still is chosen before the motion you're analyzing, all the times are positive. It's just saying we click on the stopwatch 5 seconds before he leaves the house. So when he leaves the house, your stopwatch always says +5, already says +5. You know what I mean? Just like if you're timing the 100 meters, at a track meet, and everyone else starts their stopwatch when the race starts, but you decided you were going to start your stopwatch 5 minutes before and go get a hot dog or whatever, and then you read then their 100-meter time, and it says 5 minutes and 12 seconds or whatever. They wouldn't be very happy with your timing, but you can do it. Okay, so here's the number line. And we have to figure out, so that's still the house. I'm going to do it. I'm still going to do it this way. Okay, so this is still the house. This is the hydrant. And this is the car. And the motion still is the same, right? Nothing changed about, so the person still does this. Okay, that didn't change. Now we have to use these new zeros and directions and stuff to label the places in this motion. Position equals 0 is at the hydrant, so I'm going to call that 0. Positive direction is toward the house this time, so the positive goes that way. The house is, the house and the hydrant are 15 meters apart. So to get to the house, you're starting at the 0 position and going 15 meters in the positive direction. So what's the numeric label for the house? That's 15. And it's 10 meters between the hydrant and the car. And to get to the car from 0, you have to go in the negative direction. So what's the numeric label for the car? Yep, -10. Okay, so now let's put the let's put the times on this. If your 0 time was 5 seconds before the person started walking, what's your time when the person started walking? Yep, that's 5. It's 5 seconds. Now it takes, what did I say, 15 seconds to get to the car? Okay, so I don't remember. Okay, so it's 15 seconds later than this. Oh yeah, right. So it's 15 seconds later than this. So what's the time when the person gets to the car? 20 seconds. And then it's another 10 seconds to get here. So what's the time here? And so now we can do this table again. So here's the time column, position column. At time equals 5 seconds, the position is 15 meters. At, we don't know at the hydrant, at 20 seconds, the position of the person is negative 10 meters. And at 30 seconds, the position is 0. Yep. Okay, yeah. Okay. The easiest way to think about that is just think about the stopwatch analogy. So now what happens, instead of the person, you can have a person holding the stopwatch. Instead of the person going click just as they start walking, they go click, and then it's still 5 seconds until they start. So now 1, 2, 3, 4, 5, and then they start walking. And so it still takes 15 seconds from when they start to get there, but their watch already said 5 when they started walking. Yep.
So then another point that T is 0 at 15 meters.
Yes, you could. Yep. If you know, I guess maybe I would say there's not enough information. If like I just did it there, that's right. If they just stood there, but as far as you know, they might have been in the kitchen still at 0 seconds or whatever. Okay, so now we have 5, 10, 15, 20, 25, 30. That horizontal is time. And for position, we have -5, -10, and +5, 10, 15. Okay, so first, at 5 seconds, the person's at +15, so that's a point. At 20 seconds, the person's at -10, so that's a point. And at 30 seconds, the person's at 0, so that's a point. And so the graph looks like this. So compare those two graphs. Notice that two things happened to the graphs when we made those changes to, well, actually 3 things in this case. Happened to the graphs when we changed our 0 position, our positive direction, and our 0 time. changing the 0 time made the second graph shift over horizontally. You see that? Like if you look at the starting point, the second graph is just shifted this way. Changing the 0 position had the effect of shifting the graph up and down. In this case, it shifted, like if you just look at that starting point, it shifted it 15 meters up. And then changing the positive direction had the effect of flipping the shape of the graph. You know, it was like this, it flipped upside down because we chose the 0 position, or we chose the positive direction. Yes.
So for graphs like this, is the assumption that
No, I just, so you can do whatever you want. If you want to say he did that, that's fine too. We just don't know, so. Yeah, we don't really know. So I'm not going to like dwell on that stuff when I ask these questions. But there will be questions sort of like this on, this would be a weird way to draw it, that blue line, but probably, I mean, I think anyone would agree that a more accurate way to draw it would be sort of like something that's sort of curved the whole way. But as long as you get the points right and then the graph just connects the points, that's all I really want. Like what you would have to do to change, to make it flip or whatever. No, all I want you to be able to do is come up with the graph based on the motion and then the position and time stuff that I give you. You guys want to try one? Okay. Okay, so let's think of a pendulum. There's one almost exactly like this on the practice problems, I think. That's all right. Okay, so this pendulum is going to swing. It's going to start out in this position. And it's going to swing 0.1 meters to the bottom. In 1 second. It's going to swing another 0.1 meters to the right in 1 second. And then, back, it's going to retrace its steps. So 0.1 meters to the bottom in another 1 second. And 0.1 meters to the left in another 1 second. The middle, yeah. So let's say that the position equals 0 is going to be the bottom, the middle. The positive direction is toward the right. And 0 time is when the motion starts. So see if you can come up with a position versus time graph for that. And feel free to talk to each other about it, ask me questions if you get stuck. It's just, this is just sort of a way for you to see if there are areas where you're getting stuck and get them fixed while we're all together. Oh, draw a position versus time graph. All right, so the motion is something like this, like the pendulum goes there and turns around and comes back. Okay. We have 1, 2, 3, 4, 5 points that we're given information about. And it says that 0 position is at the bottom, so we know that the label here is 0. It says positive direction is towards the right, so that's positive. So this point all the way at the right is 0.1 meters in positive direction from 0. So that should be labeled 0.1, positive 0.1. And then this point over here is 0.1 meters in the negative direction from 0. So the label for this should be negative 0.1. And now the times, 0 time is when it starts to swing. So this is 0. And then every point, they're all 1 second apart. So this is 1 second, another second, another second, and then it ends at 4. Any questions about that? So to make a table, we start at time 0, position negative 0.1. Then we go to time 1 second, position 0. Then we go to time 2 seconds, position positive 0.1 meters. Then we go to time 3 seconds, position 0. And then the last one is time 4 seconds, position negative 0.1 meters. So 0, 1, 2, 3, 4 seconds. And there's positive 0.1 meters, negative 0.1 meters. This is the position, this is the time. So at time 0, we're at negative 0.1. At time 1 second, we're at 0. At time 2 seconds, we're at positive 0.1. At 3 seconds, we're at 0. At 4 seconds, we're at negative 0.1. And you get something like that. Anybody have any questions about that? Okay. I'll put up some more problems and see you Thursday. Oh, remember, there's no labs this week. I will be in the lab room if you want to come talk to me like it's office hours or something, but there's no lab this week. Okay. Right. Oh, yeah, there is a quiz on Thursday. Yeah. But just the stuff I say, not the, not working on problems or anything.
On Thursday.
Okay.
I was wondering what I missed.
Well, it's all on D2L.
Okay,
So,
good.
yep.
Thank you.
Yep. Hi.
Hi. If someone were doing like